Okay, sorry for interruption because of internet connectivity. Am I audible to you?
Yes, sir.
Okay, so we are learning about the signal space representation of the QPSK signal. So you can see that we can represent this QPSK signal mathematically as a uh, ST or either of the terms you can use VMT, that is square root of 2 ps cos omega naught t plus 2m plus 1 pi by 4. We know that it is a quadrature, so pi by 4, m is 0 means pi by 4, m is 1 means 3 pi by 4, m is 2 means 5 pi by 4, and m in 3 is 7 pi by 4. So it is limited up to 3 only. Huh? Okay. Do not increase more than this 4, 5, 6 like this. So using two orthonormal signals or orthogonal signals, there I have used the phi 1t terms, or you can use that u1t also. It is mentioned in that particular book I have taken. Either of the symbols you can use. It is depend upon you that what you want to write. Both are correct and meaning have the same. So u1t is square root of 2 upon t cos omega naught t. Ut is the another orthogonal sin omega naught t. And when you have to be combine this on this particular equation, you have that cos a plus b. This is the equation is cos a plus b. You are familiar with this equation. There's cos a into cos b minus sin a into sin b. So using the same formula you have to be used here to derive the VMT here, that is the QPSK signal. Okay, so it would be equal to square root of PS. Uh, Actually, one step I have skipped out here. You can write also directly this term first, square root of 2 ps cos omega naught t into cos 2 pi 2m plus 1 uh, pi by 4 minus square root of 2 ps into sine omega naught t into uh, uh, sine 2m plus 1 pi by 4. This is the first term, and after that you can write this term is there, where I have just include the 2 upon t term here because we are talking about the carrier signals. So here just you have to multiply with the square root of t and divide with the same. So you will be got this term square root of ps t cos 2m plus 1 pi by 4. This is the one term. Second term is square root of 2 upon t cos omega naught t. I have just converted the above equation in terms of orthonormal signals. Similarly for the sine equations as well. Okay, and then we have to be got this first term would be nothing but the even term. Okay, and the first term after negative sign, it is a odd term v naught. Okay, and you can write this equation of the QPSK as well. Uh, this is square root of EB BET U1T. Okay. Then square root minus square root of EB B naught T U2T. This is you can write like this as well. Okay. So you can say it is we have written up to the equation number 3, so it is a 4. Then it is your equation, that is equation number 5 as well. Okay, and then finally you can see the equation number 6 as well. Okay, so in this way you can derive the signal space equation for the QPSK signals, and then further you can plot this signal space diagram. It is little bit complex as compared to the BPSK and the BFSK signaling, you can see here. So as per the phasor diagram, we will refer the phasor diagram again. We have to be see here. This is the u1 or phi 1t, that's the cos omega naught t axis, and this is the sin omega naught t axis. And okay, this is the minus sin omega t, and this is the minus cos omega naught t. Okay, and these four symbols of the QPSK would be located on this in between of this orthonormal signals. The quadrature axis are there actually. So it is 1 1, then it is, you can say it is 1 1, this is your 1 0, this is your 0 0, and this is your 0 1. Okay, and these are the four location of the signals of the QPSK, that is having the amplitude of the square root of ES, that is square root of 2 PSTB, and like this you can 2 TB means TS symbol period. So in this way you have to be represent the signal space diagram. The important term is here that we have to be find out the Euclidean distance, that you can find out this Euclidean distance is here, that is nothing but your this distance. It is your Euclidean distance between the two symbols distance. It is a equivalent distance. D is here equal to what? Square root of ES square plus square root of ES square again. Okay. So I just omit this. Just take the screenshot quickly. So I would move further the equation of the equivalent distance. Only the term is that we have to be used. Okay. So the equivalent distance is by using this formula, and finally would be got the value of the equivalent distance, that is D is equal to what? 2 square root of EB, or you can write in terms of 2 square root of PSTB as well. So either of the way you can use this to find out the writing the equivalent distances here. Okay. So this is up to the, you can say, the signal space diagram of the QPSK signal. Then finally you can write the bandwidth of the QPSK signal as well. So for that, this is the spectrum of the PSD diagram of the QPSK signal. That is, you can see the about the center frequency, the maximum amplitude is there. That is 2 PSTS, and that would be further distributed on the frequency axis. That is first 1 upon T was symbol period, and then this is the 2 upon Ts, like this, uniformly distributed here, and the amplitude would be decreases as you increase the frequency. Okay, so this is the common pattern. So for this here, the bandwidth is highest frequency minus lower FH minus FL. So it is 1 upon Ts minus 1 upon Ts, that is 2 upon Ts, or Ts is 2 TB, so you can write it as 2 upon 2 TB, that is 1 upon TB, or finally you can say it is FB. Bandwidth is smallest minimum as compared to BPSK is 2 FB, but it is here you can see that FP. BPSK it is 4 FB, but it is decreased and it is the reduced bandwidth is reduced. In this way we have seen the bandwidth is requirement is less. So it is a very good technique for transmission of the digital signals. Okay. Only the disadvantage of this is the generation and detection a little bit complex, but bandwidth is decreases, noise immunity is good, low error probability is there, and data transmission rate is high. That is the advantages of this QPSK technique is there that you can use. Okay. So also take the screenshot of this diagram as well. This is up to the QPSK. Now we have to be entered into the era of the A-Murray signals. Still we have discussing only the binary signals. Now we have to be entered into the A-Murray signal that we have learned in the previous unit when we have learning the line coding technique. So A-Murray signaling means we have to be combining the bits into the one symbol. Okay. So the time is 5 minutes. I would be just introduce it. Then we have to be continue this same topic on the next lecture, that is A-Murray, PSK, and then quadrature amplitude modulation. That is also QAM is one of the very important techniques that we have to learn in the next lecture. So in BPSK, we have that we have to transmit each bit individually, and depending upon the value of the BT, means logic 0 or logic 1, we transmit one or another sinusoid of the bit period of TB, and this sinusoid differing in phase by 180 degree, 2 pi upon 2. The formula you have to be important. You think that why sir is written like the 2 pi upon 2, why not written directly pi? But I will come to the point why I am writing like this. We have to generate some formula from there. In QPSK, what we have done, we have lumped two bits together and make one symbol, and depending on which the 4-bit words would be developed, 0001, 101, 11, and we transmit one after another of the 4 sinusoids of the duration 2 TB, and the sinusoids differing in phase by the 2 pi upon 4, that is 90 degree. Okay, in the BPSK it is 180, QPSK it is 90 degree. So if you have to see, there is a pattern. It is differ with each other by the 2 pi upon some numerical value. Okay, that is 2 raised to the power n or m. So if you have to be, when we have to be lumped, in the previous case in the QPSK we have lumped the 2 bits. Now we are, if we would be lumped the or combine the n number of bits, capital N number of bits, so that what happens in this n bit symbols extended over the time, that is it would be bit period would become now n TB. In the QPSK it was the 2 TB only, because we have combined the 2 bits only. Now if you have to become an n number of bits, it would be become n TB. and here the 2n is nothing but your uh, actually not 2n, it is 2 raised to the power n actually. Okay, so 2 raised to the power n, just correct this, it is 2 raised to the power n is equal to m, possible symbol is there. Okay, so now let us represent the symbols by the sinusoid of duration ntb, that is equal to symbol durations ts is here now ntb, which differs from one another by the phase 2 pi upon m or 2 pi upon 2 raised to the power capital N. Thus, in M-Array PSK, waveform used to identify the symbols are written as st is equal to square root of 2ps cos 2 pi f naught t plus phi m. So here m is what? M is equal to 0, 1, 2 up to the m minus 1. Okay, this is the representation of the M-Array PSK. Okay, so you have to be see little bit how the changes has been done. Okay, so between the PPSK then QPSK, again only the phase has been be added. Now what is the phi m is here? What is the formula of phi m? If you have to be see, phi m is nothing but 2m plus 1 pi upon m, that we have discussed. In the BPSK it is 2 pi upon 2, then 2 pi upon 4 QPSK, then MRE 2 pi upon m. So 2m plus 1 pi upon m is shown here. Okay, m is to the raised to power n. Okay, so and the representation of this particular phase has been shown, and the symbol points in the signal space diagram you have to be see. So this is the orthonormal signal, that is u1t or phi 1t, you can refer here. Okay, this is your u1t or phi 1t, you can see 2 upon t ts cos omega naught t. This is the phi 2t, you can see square root of 2 upon ts sin omega naught t. This is orthonormal signals. And in the case of M-Array PSK, each symbols in this signal space diagram would be separate. Please fill up the attendance simultaneously. There's only 1 minute is remaining. So these symbols in the signal space diagram has been separated out from each other with the amount of phi upon m, phi upon m to pi upon m, then depending upon the value of the m is there. Okay, then 3 pi upon m, like this it would be increases and increases like this, but the minimum distance is pi upon m is there. Okay, so this is the graphical representation of the MPSK, M-Array PSK signals are there, and from that we have to be also find out the distance of each dot or each symbol from the origin, that is square root of ES or square root of PSTS. So next lecture we will be continue this discussion, find out the Euclidean distance of this technique, and generation and detection of this M-Array PSK. So thank you all of you for attending the lecture today. So maybe next lecture is the last lecture of the 5th unit.